In this, the third part in our C++ exploration, we're going to finish off looking at constructors and destructors. Here we'll introduce firstly what a destructor is, and then we'll tie the whole thing together. Hopefully we'll tie it together. So when we think about destructors, in essence a destructor is simply a method that gets to be called, and it determines how it is that we safely and appropriately delete, get rid of, free up, destruct an instance of a particular class. That's what's known as a destructor. Why do we need to have them? You can see a few examples down at the bottom. I mean, in most cases we use a destructor where the class has, when we're creating the class, it has dynamically allocated some memory that it's using itself. And we would use a destructor to make sure that we always safely delete and to free up that memory. It can also be used that if you have a class that establishes, say, network connections or opens up links to databases or things like that, then again, these are things you will want to sort of safely close down. And you'll probably have a close method that the programmer can sort of call directly, but if they don't do that, you would still want to make sure that whenever you are destroying the instance of the class, you check to see, have I any open connections, for example, and if so, then shut them down appropriately. The syntax for a destructor, you can see here up on the sort of the top hand side, is very, very similar to a no argument constructor. The only difference is they use the sort of the tilde character. So we have a class called foo, so the tilde foo then is denoted to be the destructor class. Somewhat obviously, destructors, they are no argument methods. They are called automatically whenever the class is being removed or freed up from memory. So we don't need to call them explicitly. They're called automatically. A call to them will automatically be put in when the compiler builds the code. Again, somewhat obviously, as they're no argument, you can only have one destructor per class, and it's up to that destructor to work out if you can have different configurations of the object, what one's the right one to use. You do get a default do nothing destructor, and it does nothing, so it's not really of great use. We're going to have, destructors fairly straightforward, not that difficult, but we're going to look at areas now for constructing and destructing objects that may be problematic, and this will tie in the need to make sure that we link constructors and destructors together. So we have an example here. We've got a class called foo. You see it over on the top left. A number of one public data item, which is a pointer to, it's going to be an array of data. Line 5, we've got a parameterized constructor. You can create the class, you can specify a size. If we do that, we then allocate an array of ints on the heap of that particular size and link it through our data pointer. So this is a simple class that does actually make use of dynamically allocated data. In line 6, we have the definition of the destructor for the class, and this is sensible because we have allocated memory in the heap. We have to make sure then that we have a corresponding delete for the new that we deallocated, and that's what we do as part of the destructor. We're deleting, it's an array we're deleting, and it's whatever data points to. So far so good. That looks to be a perfectly sensible setup. Let's have a look at the test method just under it, which will highlight a problem that we have with this particular formulation. In line 3, we create an instance of foo linked to an array of 10 ints. In line 4, we're using the copy constructor. We're creating a second instance of foo called b, and we're constructing it from A. So it's the copy constructor. We haven't defined one above, so we get the default copy constructor, which does a member-wise copy from one, all the data items from one to the other. So what that means then is that whenever the copy constructor has finished, we'll have two instances, A and B. A will still point to its array of 10 data, and when we were constructing B, we copied the pointer So B will also point to exactly the same array of data. They're now sharing data. And you can see the example over on the right-hand side that A and B will be declared in the stack, have their data pointers, but both of them will point to the same chunk of memory on the heap. What this means then is in line 5, if we change data through A, and line 6, if we then print out the data through B, because we're accessing shared data, then we're going to get the same access and lookups from both instances. And line 7, so whenever we exit out a test, we're saying here that the program will also crash at this particular point. The reason for that, it comes down to how the destructor kicks in. So let's assume that A and B have now gone out of scope. The block of code that associated with test has expired. So we will free them up from the stack, and because it's a class, because it defines a destructor, then we'll automatically call the destructor on it. So let's assume first of all that A gets to be freed up first. So A's destructor gets to be called, and quite rightly, quite appropriately, it'll say, okay, I'm pointing to an array of tenants on the heap. Let me go on to free up that memory, and that'll happen. And that's great. A has been suitably, safely destroyed. When we then get on to B, B's destructor will also be called, and now B will still have a pointer to some memory on the heap. The problem is what it points to is not allocated in memory. It's been freed up. So we will still try though to free up the memory a second time, except that will not be marked as allocated memory. So at this point we will have a crash that we'll be able to work out that we are trying to free up memory that has never been allocated in the first spot. That's obviously an issue, and the program will come to a halt at that point. If we think about assignment, believe it or not, it's actually worse than the direct copy construction. So in this case here, we've got exactly the same foo class. We're not changing foo, but our test method differs slightly. So at line 3, we're creating two instances of foo, 1A and 1B, and they both happen to point to arrays of size 10. In line 4, we're using the copy assignment constructor. So B is equal to A. So we're copying, and it's the default one. We didn't define a copy assignment constructor within our foo class, so we get to use the default one that's available. So all of the properties within A get to be copied across to B as a shallow copy. Now, once we've done that, you have the fragment of code that's shown over on the right at the bottom. We have actually ended up orphaning memory. That B did point to its own, have its own pointer to a valid array of tenants in this case, but we've now overwritten that with the one that A contained. We didn't free it up, which means it's still allocated on the heap. It's lost memory, it's orphaned memory. So line 4 rather, is introduced a memory leak. 5 and 6, where you're accessing it, still gives you the same functionality as before. All of this is somewhat moot, as in 0.7. It's going to crash because we're still trying to delete the same chunk of memory once. So in this case, we not only orphan memory, we, same with a similar one, try to delete it twice, which we can't do. So this is examples of where we're not careful in terms of how we create a class, that we can end up where certain forms of usage will result in significant issues, be it memory leaks, be it crashes all out. So we need a way of trying to rectifying or to deal with this situation. How we can easily deal with it, and what's fairly standard within C++, is known as the rule of 3. That if you, in a class, think to yourself and find yourself writing a destructor, or if you find yourself writing a copy constructor or a copy assignment constructor, any of those three, if you think there's a need for one, almost certainly there's a need for all three. So these are ones where if you think, okay, I better add in a destructor to free this up, you better also add in a copy assignment constructor and just a copy constructor as well. So rule of 3, that'll keep you nice and straight. It means then that the types of cases that we looked at in the previous few slides, you'll have an opportunity to put in a specific copy constructor which will appropriately do a copy of the object, so it's not going to mess up when things are destructed. We'll finish this exploration of constructors and destructors by bringing it all together, showing you one example of a simple class, but one that contains all of the different types of constructors and a corresponding destructor. You can see the class definition here. So effectively the header file, if you like, fits on a slide. So it's some class, doesn't really matter what it is. We're declaring public private section, just by the way, the private section down from line 12 and below. We're assuming here that this class basically just points to an array of data and knows the size of the array that it points to. So it doesn't do anything useful, but this is our functionality. What we're more interested in is what above. So in our public section, we declare a number of things. In line 4, this actually is a default constructor. It looks like a parameterized constructor, and indeed there's a parameter that can be passed into it, but it also has a default value. So if you try to construct some class and you don't pass in any properties, then the constructor shown at line 4 is the one that gets to be called. So effectively it is the default no argument, or can act as the no argument constructor. Line 5, we're passing in a constant reference to another instance of this class. This is our copy constructor. Just as a reminder, it's constant in the sense that we're not going to change the thing that we're copying from. So that's line 5, sorry. Line 6 then, we have a move constructor. And you can see here we're passing in, there's not a reference, but we had in an extra ampersand character, so it's basically viewed as a reference to the other one, but this is using a move semantic as opposed to a copy semantic. You'll notice here we're not using const, and that's important because the whole notion of move is that if you take data from the other class and you're transferring ownership across, for example, to your class, then you need to make sure you actually break that linkage in the other class, that you're severing its link to it. So the move constructor does end up changing, or probably will end up changing, the other class, whereas for the other copy ones, we don't change it, it's just read-only. Line 7, you can see here that we have overloaded as a signature for overloading the assignment operator. Again, we're passing in a constant reference to the other object, and we're returning a reference to the particular class that we have to permit forward chaining. Line 8 then is just a standard parameterized call. This one here will pass in the size and also an existing array, and then copy from that. Line 10, we have our destructor. No arguments going into that one. So by way of the implementations on these, we'll just go through them in turn. The default constructor, you can see it here. All we're doing in this case is we're storing the size, and we're creating a new array on the heap of the appropriate size and storing our pointer to it. Doesn't do much. The parameterized constructor more or less is the same. In this case here, we don't want to, we're not stealing the array of data that's been passed in, we want to copy from it. So we also create an array of an appropriate size, and in line 5, this is our opportunity to copy from our input data array, and we copy the values across. A little aside, generally if you are copying within C++, one array to another array, it is normally always a good idea to use the built-in library. So here we're using the standard template library and the copy function within that. The reason for that, as opposed to, for example, writing your own for loop, is that these methods are highly optimized. Quite often they include embedded assembly. They'll run faster than the for loops that we would otherwise write. Next up, we have our copy constructor. So you can see here that when we construct it in line 3, the default initializations then are storing the size and storing the location of a new array, which we just allocated on the heap. In line 5, because we want to safely, we don't want to do a deep copy, we're going to the other instance and we actually are copying out value by value everything it contained within its data array into this object's data array. Underneath that, we have our move constructor. And you can see here it's a little bit more simple. In line 3, we actually store directly the two values within the other class, the size and the pointer to the data. So it did point, or it still does point to an array of data. We're taking that pointer, we're transferring ownership to this instance. And then in line 5, we're going to the other object and we are nulling, setting it to 0, its pointer to the data. So it loses its access to it. And that's good because then it can't modify it or try to delete that array. Last one then for the copy assignment operator. You can see there's a little bit extra to this. So this is a case where we're assigning A is equal to B. So A is going to be an existing instance. It's going to have its own data that it manages already. So the first thing we do in line 4 is that we get rid of our existing data. We free it up from the heap. We don't want it to be orphaned on it. So we delete it as an array of data, and that means that this class then has released its dependent data. 5 and 6, fairly standard stuff. We're then copying across the size and the pointer, or creating a new array of data and storing it. Now you could have done other things in here. You could have checked to see if the two data size arrays were the same. If they were the same, then you wouldn't need to delete it to create a new one. So there are ways you could potentially optimize this. Line 7, we do a copy. And line 9, because this is an assignment operator, it supports forward chaining, we return a pointer to ourselves. So we can chain it then, A is equal to B is equal to C. Bottom then, we finally have our destructor. All we do when we call the destructor is that we delete whatever allocated array of data that we have. This one assumes that we always will have an array of allocated data. Actually, you need to be slightly cautious with this here, that if you want to do it properly, so if you could null the data pointer, for example, we did this in our move constructor, you would have here that if the pointer isn't null, if we're actually pointing to something, then delete it. And if the pointer is null, then it already has been freed up. We don't need to do anything. That implementation, it assumes that it will always have an array of data, and that's maybe not a particularly safe assumption. Take away in this, couple of them. Most certainly we should all adhere to the rule of 3. It will provide more bug-free programs. Destructors, they're important. They give us a way of freeing up data that we have dynamically allocated. So in quite a lot of classes, anything that you generally dynamically allocate data, you'll probably be looking at having a destructor available within that class.